All right, welcome back, everybody. Oh, let me check if it's recording. All right. So welcome back, everybody. We'll continue. A few words to show you for the database book, because I felt a feedback I felt a bit bad for just saying, you can just maybe find it on the internet and so on. So to answer your question, you can go to library.ethz.ch right here, and then you can type, for example, database complete book, like here, and then you can do the search, and then you see mehrere Versionen. I don't know if there's English. Maybe you can also put it in English, but this has multiple versions. Then you can click here, and then you see online verfügbar, so it means available online. Then you can click, and then you have this repository here of ebooks. You can download maybe chapter by chapter, so it says 40% and so on. And normally, if you go there, you should be able to access it, right? Does it help? Yeah. So you can yeah. The second link is better. What is the second link? Pearson EBS. This one. Ah, okay. Yeah, and Pearson EBS is better. This is the one you mean? Yeah, we are waiting for the answer. Yes, that's the one. Yeah, yeah. So that exactly. So here, looking. So yes, exactly. And then if you click read. Oh wow! I don't even need to log in or anything. Just on the ETH network. Oh, there you go. Yeah. So that. Yeah. So that's it. You can just do this, right? So it means you don't have to buy anything. You don't have to look it up somewhere else. You can just find it in this way, right? So I wanted to show you that. Perfect. And thank you for asking, by the way, because that was an opportunity to show you this. Okay. So now I need to switch back to the other presentation. I just have so many windows open that I need to find the right one. So this one. Maybe if I delete it and then screen share again. There you go. There you go. Now we have it. Yep. I think there's a further question. What login does one need to read it? I think it seems to have worked just because I'm at ETH. So if you're on the ETH network or you go to the VPN, use the Cisco VPN of ETH, then it should just work. That's the idea, right? And the Cisco VPN can be found in the ETH IT shop, or you can just be on campus like where I am right now. All right, perfect. So very good that the question was asked and that I could show that to you. All right. All right. So now we are in the next part. So we just had a practical part on SQL, and now we are turning back to the math. So this is the relational algebra. It sounds like a very serious name, but don't be scared. It's actually simpler than it seems, but above all, it's very, very visual. But I had selected, yes. So where we are formally in the theory is that we define the relational table as a set of maps, which is a collection. And we threw in three restrictions. It has to have relational integrity, it has to have domain integrity, and it has to have atomic integrity, right? And this, what you see on your screen, is a relational table. So now that we have defined the relational tables, we need to specify how we manipulate them. And when I say manipulate, I mean like numbers, like you manipulate numbers with addition, multiplication, and so on. So this is called the data manipulation language, DML, as opposed to the data definition language, DDL. even though technically I showed you a bit of DML in SQL, because when you insert tuples in a table and when you modify tuples and delete tuples, technically you're already on that side, right? But that would be create table, alter table, and so on would be data definition. All right, so on the left, you have the relational model, sets of maps with the 3 constraints, and what we are going to do now is the relational algebra. Have I already talked to you about Évariste Galois? No? Okay, so I will talk about Évariste Galois. He's a French mathematician, and he had a crazy idea. The crazy idea was to, you know, when you have numbers, you can add numbers like 2 plus 2, you can multiply them like 2 times 3, and then that produces another number. And what he said is, let's abstract from this. Let's just take sets of anything and define plus or multiply on these sets, but in a very arbitrary way, an abstract way. That doesn't need to be exactly the addition of numbers. Like, then you can work on the properties of these operators. For example, can they be commutative? Can they be associative? Is there a neutral element? You can ask all of these questions. He wasn't taken very seriously at the time. Like the reaction of the mathematicians at the time was that it's just a toy and it's useless and that doesn't bring you very far. But as it turns out, he had just invented group theory, you know, all the what revolutionized mathematics with groups, rings, fields, vector spaces, all these mathematical structures. And the impact of what he did was enormous to every domain like quantum physics and so on. Unfortunately, he died very young, I think at 19 or 20. So you can imagine if he had lived longer, all he could have created, and maybe the world would be totally different right now. But anyway, because of this, that we know that it doesn't have to be numbers, we are just going to do the same thing. You know, you can do it on matrices too. Matrices are actually sufficiently generic to represent any finite groups, which is pretty remarkable. I think it's called representation theory. But we are going to do it on tables. We are going to take a table, take another table, and then have an operator, and that gives us another table. So just like numbers or matrices. So it's pretty exciting to do these things. First, we are going to work on unary operators, meaning something that takes a table and then outputs a table. And then we'll look at some binary operators that take 2 tables and then produce a third one. Let me give you the reference menu of what we have. We'll have set queries where we will do the union intersection of subtraction of tables. Since you know that a table is a set of maps, it's a set. And so the union of sets, the intersection of sets, and the subtraction of sets actually makes a lot of sense. Then we'll have filter queries where I want specific rows or specific columns of my table. So that's called selection projection. Then I'll have renaming queries if I want to rename a relation or rename an attribute, but not as an update like was done in SQL, as an operation on the table that takes a table and produces another table. Then the fourth one is shuffling queries. So these are the very computation-intensive queries that are going to push your CPU to 100%. If you want to aggregate data or you want to sort data, of course, sorting data would require a list of maps, semantics, and not just set of maps. And then we have the joining queries that are also very powerful that allow you to combine tables in a meaningful way. So remember, a relational table looks just like that. I'm going to do everything very visual on this. I just need to mention one thing, is that normally in math, when you assign a variable to some object, the object doesn't know that it has this name. If you say x equals 2, then 2 doesn't know that it was assigned to x, if that makes any sense, right? But since it's a bit computer science-y, what we are doing here, then we tend to consider that a relational table knows its name, meaning that if you call it R, then R is also included in the table itself. So that's that this concept is called a rel-var, right? So the relation knows its name. Again, it's borderline mathematical to do this, but all you need to consider is that you need to extend the concept of the sets of maps together with the name, basically, if you want to do it rigorously. All right, so I'll start with the set queries. Who is ready? Okay, then I'll go ahead. So we need two relations, but I need a bit of theory before I do this. If I have a set that has a few elements right there, I might have some operator on this set that takes one element and returns another element. For example, we could use a symbol like tilde. It's just an example. So if you have x, that's tilde x. Maybe this would give you this too. Maybe this would give you this. This would give you this. So every element in the set A is mapped to another element. You can also view it as a function from A to A, right? That maps an element of A to an element of A. But the thing is, this tilde x is still in A. You're in A and you're still in A. You might have cases where you have a function to somewhere else where the tilde x sometimes sends you in A, but sometimes leaves A. So a constraint that we have that's called closure, that we want A to be closed under tilde, that means that all of its elements via the tilde operator remain in A. For whom is that clear? Right, okay. And we can say the same thing with binary operators, like if you have x and y, then x plus y should also stay in A. That's called, it's closed under addition in that case. The reason I'm doing that is that when we take a table and another table and we do the union of two tables, we would like it to still be a table. So it means that we need for the set of all tables to be closed under this, right? And this is where it's not actually the case, and I will show you an example of that. So here's a relation R on the left and a relation S on the right. They have different schemas. Can we compute the union of these two relational tables? Well, there's can we do it? That would be the first question. And second, would it still be a table? Let me split it in two questions by raising hands. Who thinks we can compute the union of these two tables and get whatever we get? One raised hand, two raised hands. Who thinks we cannot? A third raised hand over there. Who thinks we cannot? We also have a few raised hands, a bit less. Okay. And my second question, if you think we can, do we get a relational table? Who thinks we do get a relational table? Who thinks we do not get a relational table? Many raised hands. Okay, so you're exactly right. This is the idea. We have two sets, so computing the union of two sets is always possible, right? You take a set and another set, you can always make the union. So since a table is a set of maps, we can compute the union, and we get something like this. So this is the union of the two sets of maps. Who can tell me why it's not a relational table, even though it's a set of maps? Exactly, it breaks relational integrity because the support here is AB and here the support is CDE, so they do not have all the same support. So we can compute the union of two tables, but it would not always be a table. That is the issue that we have here, right? So in order for it to be a table, which ideally we would like to have at least in this course, in big data for engineers, it's different. Here we could totally do the union and we wouldn't bother if it's not a table. So the first constraint is that the attributes must be the same. Second constraint is that the domains should also be the same if you also want to preserve domain integrity, right? So the constraint should be the same. Regarding atomic integrity, if both tables fulfill atomic integrity, who thinks the union would also fulfill atomic integrity? Who thinks it would not? Yeah. So you're correct, it would, because if it's already atomic in the original tables, then the values will still be atomic in the resulting tables because it's the same values, right? You just take the union. So we just need relational integrity and domain integrity to be maintained. And just in case people use the other definition as a relation and not as a set of maps, in that case, you would also need to be careful about the order of the attributes. In fact, in PostgreSQL, you also have to be careful about the number of attributes. But if you use the definition as a set of maps, the order of attribute doesn't matter. So that's really only if you want to use the relation definition. Okay. So assuming we have these constraints fulfilled, which is the case right here, if you look carefully, who agrees we fulfill these constraints? Same attributes, same domains. So let's compute the union. We can just, if this one is called R and this one is called S, then we have R union S. Can anybody tell me how many attributes this table will have? 3, exactly. What would be the domains? String, integer, Boolean, because it's the same domains for the two. And how many records? How many maps? 7. So we have an answer of 7. Does anybody have other answers? Yes? 3. So you say 3. Any other answers? I'm just collecting answers right here. Try to answer. Any alternate answers? Maybe I can do it as a poll as well. So who says 3? 4? 5? 6? 7? 8? Okay, so we have a majority of 7. And I think you're correct. I was about to say 6, but this is because I have a counterexample later. So in that case, you are correct. That is going to be 7. Right here. Exactly, there you go. Is there a question?
Yes. Why does the order of attribute need to be the same?
Oh, let me go back just for a moment on that one. It only needs to be the same if you use the definition of the table as a mathematical relation over the domains. Because if you define a table as a set of maps, in a map, there is no order, right? Or,
could you repeat the question?
Oh, yes, I can repeat the, yeah, you don't have a microphone. Yeah. I can maybe give you one so that you can also speak. Because we have a question in the Zoom chat, so I'm going to repeat it. Why do we need for the order of attributes to be the same? If we take the definition as a set of maps with the 3 constraints, then we don't care about the number of attributes because it's maps. So in maps, there is no order of attributes, so we don't need that constraint. But I put it in there because there's this alternate definition of a table as a mathematical relation over the domains, right? A subset of the Cartesian product of the domains, which you find in many textbooks. But when you define the Cartesian product, the order matters in a Cartesian product, right? And so if you want to be able to take the union and still be a subset of Cartesian product, then the Cartesian product needs to be taken in the same order. So it's really a purely mathematical thing. And this is exactly why the definition as Cartesian products and mathematical relations has this issue that the order of attribute actually gets you into trouble when actually it shouldn't matter as a table, right? Did I answer your question?
Yes.
Yep. All right. Then we have this one that I was talking about. So we have indeed 7 values. The reason I was careful is that we need to be careful about duplicates because these are sets of maps. And I have a slide on which we eliminate duplicate, but I think it's because I change a value. Because I really think they're all unique, right? Foo1 true is not in there. Bar2 false is not in there. Foo3 false, it's Foo3 true. So this is distinct. And Foo_4. So yes, the majority who said 7 is indeed correct. And there are, in that case, distinct. But in that case, I changed something. I just modified, if you look at the difference between the two slides, I changed this true to a false. So it's a different example. And if I change that to a false, then they are identical. And then we would only have 6 because this is the same record. And if you take the union of two sets, if an element is in the two sets, it still appears only once in the resulting set. Who agrees? Right? All right. So the majority was correct. Intersection queries. So how many attributes? 3, you agree? The domains, string, integer, Boolean. How many tuples in the intersection? Anybody? Yes? 2, and you say also 2. Who thinks 2? Yes, you are correct. It's indeed these 2. You see, there's Foo1 true in here, Foo1 true in there, and we have the other one, Foo3 false, Foo3 false. This one is not in there, this one is not in there, and this one is not in there, so we have only these 2. Yeah. So in the case of intersection, we actually never need to bother about the duplicate elimination because that we cannot create duplicates if we forget to remove them. All right. And finally, subtraction. Who knows what set subtraction is? Who doesn't know? All right, the majority doesn't know. So if you have a set A and a set B, then A minus B would basically be all the elements of A that are not in B. That's what it means. And so we can compute R minus S. It's shown with a slight oblique bar like this, this one right here. So you basically see that these 2 are in there. And because it's a subtraction, you subtract them. So these 2 go away because they're in there. So you only have these 2 that survive. So same domain and same domains and attributes. And we only have these 2 that survive. Right. That is called a set subtraction. Yes? Yes, it is well defined. In this case, they are just not used in the computation, but this is perfectly fine, right? So in other words, S does not need to be a subset of R for this to work. It can also be just a bit overlapping and not fully, right? That's a very good question. And in fact, you have an example here that you have Foo_2 false that is not in R, but that's not a problem, and it also doesn't appear in the results, right? You might want, we'll see in the queries, the word that is used is except, R except S. So the tuples in R except the tuple in S is basically the common way to say it, right? So this is the set subtraction. So that's actually our first menu item with the set queries. And we also don't need to eliminate duplicates or to worry about them because there's already no duplicates in there. So you cannot create duplicates by just doing that. Okay. You need to be careful because if you swap the sites, S minus R and R minus S, you don't get the same results. So you need to be careful about that. Union or intersection would you can swap and it stays the same. Do you know what it's called when you can swap the size and it stays the same? Starts with a C, yes? Commutative, exactly. Commutative means that you can swap the sides. Addition is commutative. 2 plus 3 is the same as 3 plus 2. Multiplication is commutative. 3 times 2 is the same as 2 times 3. Division is not, because 2 divided by 3 is not the same as 3 divided by 2, right? It's 1.5 and 0.666 in the other case, right? So it's called commutative, but only the union and the intersection are, subtraction is not. So you need to be very careful about the order in which you specify. All right. Okay. So now I'm going to go into the second category of the relational algebra, which are the filter queries. It's again, so now it's going to be one relation. You take one relation and then you output another relation. We don't need any constraints on the input, so you can take any table. And so the first thing that you can do on a table is to project to specific columns. For example, here you have columns A, B, and C, and you might want to say you project it on just A and C, right? So A and C. So I will just have these two attributes that I'm projecting to. And how many tuples? Who says 4? So, right, yeah, it's 4, because they're all unique, right? So here we project onto A and C, and we just lose column B, right? So this is called a projection when we do that. So that's a visual where you just keep certain columns and you hide the others or remove them. And here, just to play with it, I changed the value. I think I turned the false into a true. So this was a false, and if I turn it into a true, then you might have duplicates, right? It was not a duplicate here because B was different. It was 1 and it was 3. But the other two were the same. So you might, when you project, you might have less records because of possible duplicates. Who sees that? Very good. So you might lose records, or not lose records, but have less records in the projection than in the original table. And again, that's because we have sets of maps that we have to remove these duplicates. Okay. Just for the mathematics to be a bit easier in the proofs, we can also define the projection with attributes that are not in the table, but then it has no effect. So you could add D and E that are not in the table, it just doesn't do anything. You could also say it's forbidden, but it just, for some mathematical proofs, it makes it easier if you just extend the definition to also additional attributes that don't exist. Right. But in practice, you should just avoid it. When you project a table, you should really just take attributes that are in the table. That's the way that it's done. So this is the projection. And now we have the selection, which is on the, so the projection would be on the columns. The selection would be on the rows. And the selection is done with a predicate. You cannot do a selection with names, right? Because there's no such thing as row headers. Like you have column headers, the attributes, but you don't have row headers. Somebody mentioned that during the break, and that's actually a good point, that you know, between the columns and the rows. Technically, if you have a primary key, you could consider that this primary key can serve as a row header, right? You could consider that the social security is the header of the row. But in general, you would need a predicate. For example, B is smaller than 2. If you want a predicate to identify a record, you would just say that your predicate says the AHAFO number is this. And then you locate precisely one person, right? So you can also do it in this way. All right. So if B is smaller than or equal to 2, how many records do you think would survive? 2, yes, absolutely. Which ones? The first 2, yes, exactly. I have it, yes, exactly. So we have the same domains, the same attributes, and we just take a subset, the ones that are in green, they are the ones who fulfill the tuple right here. And by the way, the predicates can have a lot of things. You can do a comparison, like greater than, smaller than, and so on. You can also have logical operators, so don't be confused. It's just and or not, right? So you can say things like B is smaller than 2, and A is greater than 1, and not C is equal to 3, right? So this is what it means. This is the scary notation for AND. This is the scary notation for OR, and this is the scary notation for NOT in computer science, but they really just mean logic, right? AND or NOT. Then, of course, you can do arithmetic. So you can say B plus 3 equals C divided by 2, right? That's another example. So you can use the operation. There's even more than that, modulo, exponent, factorial, and so on. You can use, of course, attribute names. Obviously, you want to do that because you want to select identifying records. And of course, you can use parentheses in any way you want to have some priorities, right? So that's the menu that you have for your predicates, and we'll reuse them later in SQL. It's going to be a bit similar in terms of the sort of things that you can do. There is something that I didn't say explicitly. It's the Greek letters. You notice that there's Greek letters in there. Can go back. We use pi. So pi is the Greek letter that we use for projection, right here. And sigma is the Greek letter that we use for selection. Pi projection, sigma selection, right? And when we select records, there is no need to eliminate duplicates because there's already no duplicates. All you do is you check the predicate on each record, and either you keep it or you don't keep it, right? For whom is that intuitive, that you don't need to worry about duplicates? Okay, very good. Okay. Okay, and that's the visual for selection. Then there is a bit of an extension, because now that I showed you addition, multiplication, and all these things that you can do, there is something called the extended projection. So an extended projection, it's like a projection. You can take a few columns, like here A and C, but you can also create new columns that didn't exist before. So you can say you project also on D, and D is defined as B plus 1, and you write it like B plus 1 a row D. So it's going to create a table with how many attributes? 3, yes. And which domains? String, so I agree on string. I agree on integer for this one, and in the middle? String, Boolean, integer, right? Yes, exactly, absolutely. So for A and C, it's just taken from here. And for D, it's kind of implied, right? Because if you take an integer and add 1, then it's still an integer. And so that would be inferred as an integer, right? And then you have the records, and you see now we have 2, 3, 4, 5 instead of 1, 2, 3, 4. So that's what the extended projection is doing, right? So far, so good. Everybody with me? Right? So we have done the sets, union, intersection, subtraction. We have done selection. We have done projection. And now we are going to rename. I need to give you the Greek letters, by the basically, because it's not so complicated, but we use row for renaming. So in that case, we can say that row renaming A to D of R would be a table with how many attributes? 3. Which are they, the attributes? D, B, and C, yes, absolutely. And the domains? The same, exactly, because we just changed the name we just update the name, right? And then the content is exactly the same. So what's important in here, to contrast with what I've shown you in the previous lecture, is that here we are not modifying something. We just have R. R is whatever it is. It's like this, it has A, and we are just creating another table, computing another table that is obtained from the first one by being identical except for the column name, right? So this is a mathematical operation, okay? We can also rename a relation, and in that case, you see the difference here, it doesn't have a name, but if I say row S, then I'm renaming the relation as S, and then it has a name, right? So this is for the renaming. And we're already done with the third category, with renaming, right? Are you still with me? Right? How much time do we have? 10 minutes? Maybe I can go a bit. I will let you go a bit earlier still, but maybe I can say a few words about the binary query. So the next category, not grouping or shuffling yet. I'm talking about the fifth one. So you remember that R and S are sets, right? A table is a set of map, and I can compute the Cartesian product of two sets, right? You remember what the Cartesian product of two sets is? Exactly, the set of all combinations. So the set of all pairs from the two places. So in that case, if I take all the combinations from the first and the second table, so maybe first you could tell me how many records am I going to have if I take all combinations? I have 2 in the first table and 3 in the second one, yes? 6, absolutely, it's 6, 2 times 3, right? So it's going to be 6. How many attributes do you think we would have? 5 exactly, we take them all, right? We basically combine them. So all 5 attributes, the domains we take over, and we have 6. Do you see how it works? We have this with this, this with this, this with this, and then we have this with this, then this with this, and this with this. We just do all combinations, and then we glue them together. When we have this with this, we glue it together. So technically, it's a pair of 2 maps. So you have a first map that maps ABC to foo 1 true. Then you have a second map that maps D to foo and E to 1. And you take the pair of the 2 maps. But in the database world, I told you when we do the Cartesian products, we flatten everything. So when we have a pair of 2 maps, we glue the 2 maps together. So then what we get here is a huge map that maps 5 values, right? We glue them together. And that's how we have the Cartesian product. For whom is that intuitive? Right? Very good. Cartesian products are very scary. You can just do the math. Imagine that you have a table on your disk that has 1 million records. It's a pretty common thing to have. 1 million records for R, and we also have 1 million records for S. How many records do you have in the Cartesian product? Who thinks 1 trillion? It's 1 trillion, right? 1 million times 1 billion, 10 to the power of 6 squared, 10 to the power of 12, that's 1 trillion. That's not going to fit on your laptop. So if you feel like you want to crash your laptop, open your Jupyter notebook, create 2 big tables and compute the Cartesian product, and the whole thing is going to crash. So this is, you can try actually, we do it when we check that the exam, we can still recover if you do that at the exam. Don't worry, if you do it at the exam, we have solutions, we can relocate you and something. But just so you're aware, Cartesian products are really, really something to be very careful about with large tables. Okay, so we don't need duplicate elimination. And by the way, just so you know, what if you do the Cartesian product of 2 tables that have attributes in common, like you do the Cartesian product of this and this, but they both have an attribute B, right? So it could seem that there is a conflict. And so what is done typically, since we anyway know the name, we prefix R.B and S.B. So you basically see this is the attribute B that came from the left side, and this is the attribute B that came from the right side, right? So this is also what is done in practice. It's not very elegant mathematically, but this is a way to still make it work without returning an error. Right. And of course, if you're not happy with this and want to rename them, then you can, right? You can just use row and rename B to E, and then you again have a very nice table with nice attribute names, right? That would still be a table with attributes names, just that the attribute would be the string R.B and then S.B, right? But it's just nicer like this. Okay, so that's the Cartesian product. The next thing I'm going to explain is the join, but I think that I can keep for next week because that's again a big piece of knowledge to digest. So who followed more or less today? Right, very good. I hope you enjoyed the exercises with the TAs, that you enjoy also reading the book. Now that we showed you how you can have it at the library, I really encourage you to read the chapters of the book. It's very well written. One of the authors, Hector Garcia Molina, unfortunately he's deceased now, but he has a honorary doctorate from ETH that he received I think 18 years ago. He was very well, is really good at these things. So this is a very good book. All right, so thank you very much, everybody. I hope you enjoy your early lunch. Thank you, Marcin, for moderating, and see you next week.